Hello dear learners. In continuation to our discussion about Earth's ionospheric structure and photochemistry, in this lecture we will understand aspects related to photochemistry and ionospheric variability. Okay. Right. So, in the last class itself we have seen how the ionospheric layers are defined. The D region, E region, F1 and F2 regions are defined. So, in the earlier lecture this was considered to be the ionospheric electron density profile with respect to height, and here the electron density profile with respect to height during solar minimum in the daytime is also shown. So, where you also see the 4 different regions, the F region, E region, D region. F region is a composite layer which we combinedly are referring to F1 and F2. Okay. So, there is also a variation of neutral densities with respect to the solar minimum and solar maximum. Okay. Right. So, the message is simple: solar maximum, the electron densities are highest, and solar minimum, they are lowest, and during the daytime and night time. Okay. This is the day night distribution. So, during the daytime you have all the 4 layers D, E, F1, F2, and in the night time you have only the E and F. Right. So, there is a variability with respect to time of the day. Right. So, ionospheric electron density on a global scale, if you see, it is not constant throughout the altitudes. So, the ionospheric variability has already been established with respect to solar cycle, right? Solar cycle variations. Then you have day and night time. These two variations are already explained in the last class itself. This variability is with respect to the space or spatial variability within the Earth, or this is the, let us say, one day side of the Earth. Geographic equator is passing right through, which is separating the Earth into 2 equal halves, and what you see here is the electron density. So, if you attribute the existence of ionosphere to the daytime or to the sun, solar radiation, availability of solar radiation is directly available for the entire day side. If you take the sun and earth geometry, this becomes the day. Let us say this entire part in a 3-dimensional figure, you can think how it may look. This entire is day. But what you see here is that if it is day, there is no reason to believe that the electron density is more at a point and less at a. By the way, these dark patches that you see here are basically, so these dark patches that you see here are basically the regions of electron density, enhanced electron density, right. So, you see they are not, it is not constant electron density throughout. So, here an imaginary line can be drawn which is separating these two regions of electron densities. This imaginary line becomes the geomagnetic equator, okay, just like geographic equator. This is geomagnetic equator. So, geographic, if you take the earth to be a sphere like this is the north pole and the south pole. These are the geographic poles. Since the earth is also considered as a bar magnet, its poles of magnetic field strength or magnetic poles are also there, right. So, if you put them into perspective, the geomagnetic equator is this line which is separating these regions of electron density on either sides, right. So, which means the third important variability is with respect to the spatial variability or variation in the number of electrons per unit volume versus latitude. Okay, latitude is the most easy way to bring the variability. Latitude. What do you see? You see two patches of electron density on either sides of the equator, and apart from that, apart from those regions, electron density is there everywhere. It is there, but this is a very large electron density. So, this anomaly of non-uniform electron density distribution or enhanced electron distribution around two regions on either sides of the geomagnetic equator is called as equatorial ionization anomaly. The anomaly indicates because of some process, the electron density is not same. Electron density is enhanced on either sides of the geomagnetic equator by a large volume, by a large magnitude. Right? So, in order to understand this anomaly, we may have to bring in some electrodynamics, and then only we will be able to understand. This will be a topic of discussion after like 5 or 6 lectures, but just to visualize, the electron density is not constant even with respect to the latitude. And more interestingly, if you combine the rotation of the earth around itself, or if you imagine the earth to be sitting at rest, the sun is moving, right? Sun is moving around the earth. So in that case, this ionization anomaly follows the movement of the sun. So it has something to do with the sun because it is situated on either sides of the geomagnetic equator, not the geographic equator. This anomaly has something to do with the sun, and this anomaly also has something to do with the with the magnetic nature of the planet Earth. Right. So we will combine all these aspects and then try to put forward a simple explanation why this anomaly will exist, but that will come after a few more lectures. Right. So, what are the sources of ionization? Sources of ionization as in what are various mechanisms or drivers which can produce electron density. So, what is the process? Process is simple. You have neutral species, you have energetic radiation which ionizes this neutral species and creates electrons and ions, and maybe equal number of electrons and ions. And ionosphere also has neutral species. Right? This figure shows all possible types of energy inputs, drivers which can cause ionization. So, you see here, so this is on the x axis you have the ionization rate per centimeter cube per second. So, 10 to the power of 4, if you take 10 to the power of 4 per centimeter cube per centimeter cube per second, which means the number of ionizations will be 10 to the power of 4, which means 10,000 ionization processes will happen in a unit volume per second. And altitude. So, altitude is on the y axis. So, you look at one solar UV and X rays, this one. This one is solar UV and X rays, which is most important or most dominant in the 100 kilometers or 150 kilometers. But the entirety of the most important, the most dominant ionosphere is actually existing somewhere above 150 kilometers. But nonetheless, if you talk about the lower D region or E region, the sources are many. See, the relativistic electrons originating from the sun or locally accelerated within the radiation belts contribute to a significant portion of electron density within the 100 kilometers altitude limit. Auroral electrons, the electrons which precipitate from the auroral oval or from the auroral regions, also participate or also contribute towards the formation of electrons. And solar proton events, these are driven by some complicated solar prominences, also contribute to a large extent in creating the number of or creating the electron density in the lowermost altitudes. Right. So, the essence is, the take home is very simple. There are different drivers of ionization at different altitudes. Okay. All of them cumulatively are responsible for the formation of the ionosphere or electron ion pairs. Right. Now, let us talk about some numbers. So, the ionosphere vertical density pattern shows a strong diurnal variation and a solar cycle variation. This goes back to those three important points of variability which I have mentioned. One, electron density or the ionospheric density with respect to height changes drastically during solar cycle. It is at its highest value during the solar maximum, at its lowest value during the solar minimum. One, during the daytime, the electron density is highest, and during the night time, the electron density is lowest. The third important variability was actually with respect to the height. The ionospheric electron density is not constant with respect to height. It changes that actually is responsible for the formation or for the identification of various ionospheric regions D, E, F1 and F2. The fourth important variability could be the ionization anomaly or largest electron density on either sides of the geomagnetic equator. Right. So, this is what exactly it is that is being written here. So, identification of ionospheric layers is related to the inflection points in the vertical density profile. So, the inflection points are those points where the slope is suddenly changing its direction. Okay. So, depending on those inflection points, we define the D layer or D region, which is from 60 to 90 kilometers. These are the numbers that you should always remember whenever D region, I mentioned D region, you should always think of processes which are happening between 60 to 90 kilometers. That is it. Okay. 60 to 90 kilometers, everything between these two heights is called as D region. And the peak, what is peak? This is the height at which maximum electron density can be found within D region, not everywhere, not anywhere. Okay. So, this is the height at which maximum number of electrons can be found within D region. How many number of electrons? 10 to the power of 8 to 10 to the power of 10 per meter cube. A cube with 1 meter will have 10 to the power of 8 to 10 to the power of 10. Why do I have a range? Simple. During the solar maximum, it can be assumed to be 10 to the power of 10, and during the solar minimum, 10 to the power of 8. What about the night? During the night, the D region simply disappears. That is what we have already understood, right? E region, which is immediately sitting above the D region, is known to exist between 90 to 140. So, you have to 60, you have 90, then you have 140. Okay. So, 60 to 90 is D, 90 to 140 is E. How much? The peak electron density within this D region is not at 140 or not 90, it is at 110 kilometers altitude. So, which means somewhere here. Okay, this is called as the E region. How many number of electrons? Several 10 to the power of 11. Okay. So, it can be 1 10 to the power of 11 or 9 10 to the power of 11. This window is only because of the solar cycle, let us say, or time of the day, because E region, right. F1 and F2 are the regions which are sitting above the E layer. So, F1 is the first layer, 140 to 200 kilometers. So, it is 140 to now it is 200. You always remember these values. This will be very helpful in your assignments and your end-term examination as well, right. So, 140 to 200 is F1, and peak is at 200 kilometers, almost at the top. And how many number of electrons? Several 10 to the power of 11. It can be, let us say, 8 10 to the power of 11 to almost 10 to the power of 12. You see, one order of magnitude is changing in between. So, how many number of electrons? This will be several 10 to the power of 11 to 10 to the power of 12. F2 region is what is sitting above F1 region, and it will go almost up to 500 kilometers. Okay. So, this is F2 region, and this is the most densest region, or the most dense plasma is present in the F2 region, and the peak is at 300 kilometers, let us say somewhere here. How many number of electrons? 10 to the power of 12. So, this is 10 to the power of 11, this is few 10 to the power of 11, and this is 10 to the power of 8 to 10 to the power of 10. The top side is the topmost part of the Earth's ionosphere, which is sitting above F2 layer. So, in essence, what we have learned is that 60 to 90 is D layer, 90 to 140 E, 140 to 200 F1, 200 to 500 F2, 4 layers during the daytime. These are these altitude limits. You must remember these limits, okay, and you must remember these densities, the electron density, the peak electron density in each of the ionospheric layer, right. So, what have we learned? We have learned how the layers are defined, what is the criteria to define a layer, how many layers exist during the daytime, and how many layers exist during the night time. Okay. So, just one more slide which will sum it up, sum all the, not sum, maybe it will offer more insights into the ionospheric variability. Let us go through them. Diurnal and solar cycle variations in the ionospheric density profile. So, in general, the densities are larger during the solar maximum than during the solar minimum. This has been iterated many number of times already. The D and F2 regions disappear at night time, right? During the night time, an extension of common sense simply says there is no sunlight. The ionosphere should not exist. I would say yes, some part of the ionosphere will not exist during the night time, but some part will remain. What will remain? E and F layer. We are not going to call F2 separately here. We are simply going to call E and F layer, the uppermost part of the F2, will exist, but they will not be very, very strong. They will be weak. That means the number densities will be lesser, but they will exist. Okay. Top side of the ionosphere is simply an extension of atmosphere or the ionosphere into the magnetosphere or the magnetosphere. Okay. So densities depend on the seasons, of course. Yeah, this is not what I have not talked about. In the summers, winter. So now you have to, if you have to understand this by yourself, let's not make it a lengthy session. Maybe you can understand by yourself. You bring the sun-earth geometry, you will understand why the seasons exist. The northern summer, southern winter, or oppositely like northern winter, southern summer. These seasons exist, combining the rotation of the earth, the actual tilt of the earth with the earth's orbit. You will understand how seasons exist. With regard to the ionospheric variability, even the density, the total number of electrons per unit volume, won't remain constant within a year. It varies with respect to the seasons. How? The density is larger during the summer and lower during the winter. Looking at an overview of the ionosphere. So, structure of the ionosphere is continuously changing, varies with day, night, seasons, latitude, and solar activity. Right. So, essential features are usually identifiable. Looking at the figure, you can find out where does the D layer exist. There are some techniques, but we will talk about the techniques on some other day. Okay. So, ionosphere is divided into various layers according to the electron density and altitude. D layer, E layer, F1 and F2. So, now let us talk about why do these layers exist, or why the electron density in these layers is different. Solar energy is deposited at various altitudes depending on the absorption of the atmosphere, how much the absorption is happening, how much amount of radiation is happening, or how much attenuation of the incoming solar radiation is happening. So, physics of the recombination. So, now ideally the ionosphere is a dynamic entity where continuously electrons are being produced and continuously electrons are lost, which means neutral species are being formed. The electrons combining with the ions giving the neutrals immediately. It's a spontaneous process which happens as fast as the ionization itself, right? So, you would naturally expect that these two processes will compensate each other, giving a stable atmosphere, a stable ionosphere, which is entirely made up of neutral species, but it's not the case. The recombination process depends on the density of atmosphere. Okay, so recombination not only depends on the availability of electrons and ions, it also depends on which type of ions are present and what is the rate at which recombination can happen. Okay, so not all species will recombine with electron at the same speed. Some species will recombine with the electrons very fast and some species will recombine with the electrons at a slower pace, which means you are leaving out a provision for some electrons not to immediately recombine and give you neutral species. So, some processes are slow. So, there are some electrons and ions going through that process, and the formation of neutral state for these electrons and ions is going to take a bit longer. How longer? It may so happen that this completion time or the time in which this recombination will be complete may be larger than the duration of the night itself. So, in that case, recombination will be responsible. The same process which is ideally supposed to take care of the removal of electrons and ions is now leaving out a provision for the electrons and ions or the plasma state to exist during the entire duration of the night. Okay. So, that means if you now take the species such as N2, O2, O, O3, NO, right, N. So, all these atoms or molecules can be ionized, can be dissociated and resulting in the formation of electrons. So, the total negative charge is entirely possessed by the sum total of the densities of electrons, but the total positive charge, right, the total positive charge is distributed over different types of ions, isn't it? N2 plus, it could be N2 plus, it could be O2 plus, it could be O plus, it could be O3 plus, it could be NO plus, or it could be uh, anything, many other possibilities, right? So, if you write the total polarity of negative charges, what and all are responsible for the negative charges is just as an electron. There is a possibility that you can have some negative ions, but that is valid only in the lowermost part of the ionosphere and need not be taken into account when you are talking about a generalized or a larger perspective, macroscopic description. We do not have to talk about small pockets of negative charge, which can be there in the form of negative ions. But coming back, so the total negative charge is entirely made up of electrons, whereas the total positive charge can be many N plus, N2 plus, O plus, O2 plus, NO plus, etc. Many, right? Now, if there are, let us say, 10 to the power of 12 electrons, then there are 10 to the power of 12 of these different types of ions. Not each, but sum of all these different types of, sum of number of all these different types of positive ions should also be equal to 10 to the power of 12. Now, the speed or the pace with which electron combines with N plus is not equal to the speed with which electron can combine with N2 plus. Some of them are faster, some of them are slower. What will happen? Whatever is fast, okay. So, let us say N2 plus or NO plus, electron recombination with NO plus is very fast. What will happen then? This, let us say there are like 10 to the power of 7 NO plus species, and so this 10 to the power of 7 being fast, very fast, this reaction electron plus NO plus, if this is very fast, that means it happens instantaneously. Then how many number of electrons will be removed? 10 to the power of 7 electrons will be removed, and after that there are no more NO plus available, which means the remaining electrons, 10 to the power of 5 electrons, have to recombine with other types of positive ions, which means I have already spoken that this ion recombination reaction is a very fast one, which means the other processes are not as fast as this, right. Now, if it so happens that these processes take certain amount of time, and this certain amount of time is the duration of night itself, then despite the absence of sun, despite the absence of direct solar radiations, electrons are there, they are just trying to recombine, it is taking time, that is it. So, as a result, during the night, the ionospheric electron density will exist, okay. This is an intuitive, or this is just a toy model sort of thing to explain the ionospheric density variation or ionospheric presence during the night time. We will do some simple mathematics to actually understand this in the subsequent lectures. Okay, right. Now, the composition of the day side ionosphere under solar minimum conditions, this is where it becomes specific, or this is where it becomes important for you to get these species or remember the species which are there at every altitude. So, at lower altitudes, the major ions are O2 plus and NO plus. So, at lower altitudes, let us say 100 kilometers or 150 kilometers or 70 kilometers or 80 kilometers, the major ions, the major ionic species are O2 plus and NO plus. And near the F2 peak, 300 kilometers, where the electron density is of the order of 10 to the power of 12, the most important species is O plus. Okay. So, here 300 kilometers, the most important species is O plus. And the top side of the ionosphere is dominant in H plus, because hydrogen being lighter, it tends to escape from the Earth's atmosphere and reach the topmost altitudes. Now, in the topmost altitudes, there are a lot of photons available, so they will ionize. So, on the topmost altitudes, it will be O plus, right. So, in the bottommost, you have O2 plus molecular ions and NO plus. In the peak F2, we have O plus, and in the top side, we have H plus. For all practical purposes, the ionosphere can be thought of as a quasi-neutral plasma. Okay. So, the net charge is practically 0 in each volume element with enough number of particles. Quasi-neutral means overall in the macroscopic purview, the total number of electrons is equal to the total number of ions. That is what it means. Okay. The ionosphere is formed by ionization of three major or main atmospheric constituents, which are N2, O2 and O. And the primary ionization mechanism is photoionization by extreme ultraviolet or X radiation. In some areas, the ionization by particle precipitation is also important. So far in our discussions, we have always used, or we have always assumed that the X radiation, UV radiation is responsible for the formation of ionosphere. We are telling in some areas, not everywhere. Where are those? What are those areas? They are the polar regions. Polar regions, ionization by particle precipitation is also important. All right. So, ionization process is followed by a series of chemical reactions. The total ionization, or the population of electrons and ions, are produced by a series of, followed by a series of chemical reactions. Many processes are present. So, recombination removes free charges and transforms the ions into neutral particles, right. So, this is how the ion density with respect to altitude will look like. What we have seen earlier is something which is related to the structure of the Earth's ionosphere, which is how the total number of electrons varies with respect to height. But if you look at the other side, the positive charge, what and all are the chemical species or ions which are present in the Earth's ionosphere is shown in this simple figure. Okay. So, look at this. The bottommost region is O2 plus and O plus. The rightmost curve is the ionosphere. So, the sum total of these species at any given height should be equal to the ionospheric electron density. I hope it will be easy for you to follow. The sum total of all these He plus, H plus, you take any given height, you add all the positive ion species, it will be equal to this. Okay. You go to 500 kilometers, He plus and H plus are the major ion species, and 200, 250, it is O plus, right. So, we will continue our discussion with more interesting aspects about the Earth's ionosphere in the next lecture.